Welcome to Math 317, lecture 35. We have a guest lecturer who will be talking to us about tiling rectangular lattices.
All right. Okay. So the other week I was going through Professor Miller's math riddles page and I came across the problem tiling rectangular boxes. And this is the formal statement of the problem. My math. Okay. Perfect. Okay. So I found the tiling rectangular boxes. How do I get rid of this?
You then just slide to the box.
Okay, I see. So I found the tiling rectangular boxes problem. And this is the formal statement. For each positive integer n, consider a 2 by n rectangle. It can be tiled with n dominoes where each domino is 1 by 2. How many different ways can it be tiled? And what if instead of a 2 by n rectangle, we were to consider a 3 by n rectangle? And so when I was trying to solve the problem, I was searching fruitlessly for a solution based on the combination function. And I just couldn't find any relationship between the actual number of tilings and that function. And so when I eventually became frustrated, I looked for a solution online and I found some very interesting research based on the topic, extending the problem to m by n rectangles called rectangular lattices. And those look like this. I prefer to think of them just like a standard rectangle, divided into sections. So we can say that this is a 3 by 4 rectangular lattice, but you can also draw them as a grid of points. Like this, where each individual dot corresponds to one of these squares. I think it is more intuitive like this, so I'm going to continue using that throughout the lecture. And so before we start, before we explore the findings of the research that I found, I want to define a few things. First off, the Dimer model. So the key definitions of the Dimer model: a perfect matching of a graph is a subset of edges which covers every vertex exactly once. And for our purposes, a graph is our rectangular lattice. Every complete tiling of a rectangular lattice is a perfect matching since there are exactly enough dominoes to fully cover the area. And then the Dimer model is the study of the set of perfect matches of a possibly infinite graph. So the tiling rectangular boxes problem is concerned with the Dimer model of rectangular lattices. All right, so now we're ready to discuss our first bit of research, a paper done by Dutch physicist P.W. Castellane. Where he was talking about tiling rectangular lattices of any size, n by n. So, Castellane defined the rectangular lattice as a two-dimensional quadratic lattice embedded in a plane completely covered with dimers, dimers being the dominoes that we are finding up there. Castellane then defined the 1 by 2 dominoes in terms of coordinates, lattice points ij, or that set up there, where the number of horizontal blocks occupying ij and i plus 1 and j are denoted n2, and the number of vertical blocks occupying ij and i and j plus 1 is denoted n prime 2, well, not n prime, n tick 2 or sub 2. And
what do you define n2 and n2 prime?
That has to do with the number of cells of the lattice that are being taken up by each dimer, the domino.
You always wonder why they're choosing the notation.
Right. And so the number of ways in which a lattice can be covered with blocks so that every point is covered by exactly one block is defined as G of N2 and N tick 2. When Z, I think it's supposed to have it on the slide, but it says when Z equals Z tick and equals 1. Oh wait, no, that's for the generating function. Never mind, that's later. And so this is the configuration generating function, which Castellane used or like started with in his process of calculating the number of possible tilings. And so he started with this, and then by performing various advanced operations on that generating function, he was able to find this equation, which is very, very complicated. But basically when Z and Z tick in the input for that Z sub Mn function, when those equal 1, that the output of that function for a given M and N that are not both odd, the output of the function is the number of possible tilings for that particular lattice defined by the M and the N. And then like while this equation provides an exact answer, calculations for the number of tilings for M by N lattices with large M and N are incredibly complex and time consuming. For example, I was working in like a particular graphing calculator to just see how far I could get with that function, and I couldn't get past like N equals 48 and M equals 50. After that point, I just wouldn't be able to calculate it. So there's like kind of a challenge with that.
And how close to an integer did you get when you did it?
I was always at an exact integer when I did it. That could be due to like rounding on the calculator.
I mean, it has to be an integer.
It does.
So that's impressive that the calculator was.
Yeah. So, and then next.
I have a question.
Yeah.
You know why M or like the products, it goes to 1/2 M instead of M?
It goes to 1/2 M because I think I might mention it later in the presentation, but the number of total dominoes in the rectangle that like tile it is equal to 1/2 M times N, because the area of the lattice is M times N, and each domino itself takes up 2 cells. Yeah. Okay, and then to like overcome the challenges of calculating with that function, Castellane, it provided a method to estimate the number of tilings. It's this one, right?
Yep.
Okay, good.
Just want to spark it a little bit. No, I think you're just blocking it because you have the.
Yeah, there it is. Okay. Cool. So to get his like estimate, he first defines phi sub mn to the 2 as z sub mn, our original like huge generating function, raised to the power of 2 over mn. And then he found that the limit of phi to infinity as mn.
Is that squaring it, or is that related to?
It's not squaring it. It's just the way that he wrote the notation in the paper. I wanted to keep it mostly consistent, but yeah, it is kind of confusing. Yes.
Yes, the notation is suboptimal.
Yes.
And there was no, I think, MN even in the notation.
Right. I included that so it would match up a little bit more. But so he noticed that as the limit goes to infinity for m times n, the actual limit of the estimate is approximately equal to that value defined by z sub mn of 1 and 1 to the 2 over mn. That raising it to the power of 2 over mn is significant because doing so makes the output of the function give you the number of possible positions for each individual dimer in the lattice, so each individual domino. And he found that as that the actual limit was close to 1.791622.812, which is also equal to approximately e to the 2g over pi, where g is Catalan's constant. And then if you raise that limit to the power of 2 over mn, you're basically reversing your step and getting closer to the actual value for the generating function, which will give you the true number of tilings. And that's true for like very large n's. When I was calculating on the graphing calculator, I never quite got to where it was within like an order of magnitude with like through the capabilities of the calculator. I couldn't check, but it seems to be true that it does actually approach it.
A regular graphing calculator, or were you using a program like that?
I was using Desmos.
Yeah.
Yeah. And so the values given by the estimate are always greater than the true number of tilings, since the true number of arrangements per domino is always increasing. So using the fourth function, the limit of phi to the 2 over mn is an upper bound on the exact number of tilings for an n by n lattice. And then, so that concludes my analysis of that particular paper. I'm going to move on to another one. It is a simpler approach to the tiling problem, and it doesn't rely on highly complex math like the previous one did. It was submitted to a Math Olympiad project festival by Hung et al. In 2019, and provides a method for finding the number of tilings for a 2 by m rectangle. Notice the change in the small change in notation from m by n to n by m. So this is our notation. So given a 2 by m rectangle, there are a of m possible tilings. So that's using sequence notation. There is only one way to tile a 2 by 1 rectangle. A of 1 equals 1, because the 2 by 1 rectangle itself is just a singular domino. And then, for example, a 2 by 2 lattice. There are two possible ways to tile this. You can either do it both horizontally or both vertically. And as such, they were able to calculate the total number of remaining. Well, they were able to split up larger lattices into sections that were smaller and easier to calculate. And I'll show you an example. These are some figures taken from that paper for when m is greater than or equal to 3. So the horizontal row is greater than or equal to the number of columns is greater than or equal to 3. So if you're tiling the first column, you can either tile it horizontally or vertically. So we see on the top it's tiled vertically, on the bottom it's tiled horizontally. If it's vertical, there's a of m minus 1 possible tilings for the remaining area. And if it's horizontal, there's a of m minus 2 possible tilings for the remaining area. And that shows that a of m is equal to a of m minus 1 plus a of m minus 2, which it should look familiar. That's the Fibonacci sequence. That's the same statement for that sequence. So the authors tried to find a non-recurrence formula for a of m using the characteristic equation x squared equals x plus 1. And performing operations on that gave them that x is equal to 1 plus or minus the square root of 5 over 2. And then they found that the form of their non-recurrence formula is a of m equals a of x1 to the m plus b of x2 sub 2 to the m. From there, they used the values of x they found through the characteristic equation to find the non-recurrence formula listed on the bottom there. And then that is actually the same formula that's used to find the mth Fibonacci number. And so as such, the number of tilings for a 2 by m rectangular lattice is always a Fibonacci number. Also, This formula gives the correct number of tilings for a 2x m rectangular lattice without using trigonometric functions or products, making it much more efficient than Castellan's equation, although it is less applicable to a wider range of lattices. You're kind of limited to the 2x m case. Yeah, only for 2x m. Otherwise, you would have to. They solved it for 3x m, but it was a little bit less, less interesting of a solution, in my opinion. So I omitted it in this. And so now I want to discuss my own observations relating to incomplete tilings of rectangular lattices. And so far, I've observed these relationships to be true for small values of m and n. And later, I intend to look a little bit deeper into the topic. So when both m and n are odd in a lattice, it's impossible for a tiling of the lattice to be a perfect matching because the dominoes themselves have an area of 2. The area of the total lattice has to be some multiple of 2. And then suppose we want to minimize the number of tiles left untiled, or number of points left untiled. So for example, like we want to have as few of these individual boxes to be uncovered by a domino. And so therefore we'd want to pick a point that when untiled is the only point left untiled. But I think it's a little bit harder to identify those points. So I chose to identify unwanted tiles, those which result in tilings having 2 or more, or at least a little greater than 1 points left untiled. And what I found is that for small values of m and n, points of these forms result in points of the forms I've listed on the slide result in more than 1 point being untiled. And so I can provide an example of that on this board here. So if we have a 3x3, so we have that m and n are equal. So at least I or j has to be even for it to be untileable. So for example, or for there to be more than 1 point remaining untiled after the rest of the tiles are tiled. So if we choose like this point, then to tile these 2, you have to go like that. You have to go vertical here as well in order to access the corner. But then you're left with 2 tiles remaining here, or if you went across on this one, you'd have these 2 as well. Or straight down, you'd also be left with 2 tiles. But for example, if you were to pick the middle from the 3x3, you would be able to tile it completely. As such. No. That's also true for a 5x5 and a 7x7. Professor Miller, would you like me to demonstrate those as well?
It seems similar.
Yeah, it's very similar to those ones. So I'll show a 5x3 now for the case when m and n are not equal to each other.
And then it does become an interesting question. What is the maximum number of squares that would not be hit if
Right.
you remove just 1?
Right. So we have our 5x3, or 3x5. And then for this case, we say that I and j such that I or j is even. So that eliminates, that means that we wouldn't want to pick this point. Well, actually, let me pick that one.
Like the corners.
Yeah. Wait, either. Oh, no. So we wouldn't want to get these ones. And then we wouldn't want, I think that's actually it for this case.
So what are you trying to avoid right now?
I'm trying to avoid picking points that when untiled would result in more than one point being untiled, more points other than itself being untiled.
Okay.
So either I or j is even. So this is also, yeah. So it would be those particular tiles that you can't choose without, choose to be uncovered without other tiles being uncovered. For example, if we just look at this top left one that I've marked off, start by tiling right here because you need to access the corner. And then in order to block this corner off, you have to go horizontally. And then you can continue around the perimeter.
Wait. Oh, okay, just showing.
Yeah, I'm showing like the tick marks correspond to a domino going over the points.
Okay, but you don't know that this is the best way you can go.
Correct.
So
I
agree with your second, but I disagree with you. You put your third one on the bottom row.
Right.
That's not where I would put my third.
Oh yeah, you could go across here.
You have to. Well,
Yeah.
I guess if you're trying to set it up so that that is the only thing that's left,
Right.
you would then go in the second row.
Here.
Yes.
Yeah.
And then if you can show that this still leaves you with one additional square untiled, then you know nothing can beat this. Because the only thing that could beat this is if you're fully tiled. If
Mhm.
you're being fully tiled, you have to do this.
Yeah.
So now what move is forced next?
The move that's forced would be either this one.
Exactly.
Here. Yeah. It could also be that
It
one.
could also be that, which is also forced if you want to.
Yeah. And then
I wouldn't do the vertical one. That's not yet forced.
Okay.
That's not yet forced.
This one, however, is.
Yes.
And then so you were left with kind of a dilemma here, where one of these remaining points is going to remain untiled, or two of them actually.
Wait, so what this tells us is when we were trying to keep everything tiled as much as possible, when we put that one in the second row going horizontally, that we needed to do that if we wanted to try to have everything else tiled.
Mhm.
When we do this, we're going to be left with two additional squares that are untiled. Do you have something that was better than two?
Something that was better than two? Yeah, well, if you were to pick one of the points I didn't mark off originally.
No. I'm saying if you have that X there, could you do better than two
Could
additional
I do better
squares?
than two additional squares? I don't imagine so, because as we've shown, all the moves that we made were forced up until this point.
But these were forced trying to keep alive the hope of tiling everything.
Oh, right.
So you gotta be very careful. This is not proving that the best you can do is two additional squares untiled.
Mhm.
This is saying that if we want to have a chance of tiling everything else, we have to do this.
Right. There is, for this case, there is actually another tiling that would be better,
Okay.
which I can show now.
So why don't you leave that one up and draw the next one?
Okay. We'll do that. So again, if we're picking this point right here, optimally, we can go around the perimeter. And then, oh wait,
That's still gonna leave.
no, there was one thing that I wasn't saw earlier.
Do you maybe give up on the upper left?
Yeah.
So that's still gonna leave, I think, two.
I saw one a second ago though.
How many squares are there initially?
5 by 3, there's 15 squares.
No, we lost one, so there's 14 squares available, right?
Right.
So if there's 14 squares available, is it possible that we might be able to tile everything? If there's 14 squares available, is it possible?
Yeah.
It is.
Even.
Because it's an even number. So as soon as you prove that you can't tile everything,
Mhm.
what do you now know?
You know that there's an odd number of tiles in the
What I'm
set.
saying, we have 14 squares remaining after you throw away the X. We proved that you can't tile everything.
Mhm.
So what's the maximum number of things you can tile? Of the
Um,
remaining 14 squares?
12.
12. So we know that you have to miss at least 2.
Right.
So when we showed, in that tiling on the left, that it was missing 2 additional ones, we were worried that maybe there's a better choice that's only missing 1 additional square. No, that can't be, because we know we're putting down an even number of tiles.
Yeah. And then so continuing with that, if we were to pick a point that was not on these 2 rows here, I think, yeah, those are the 2. We would be able to tile the complete lattice. So I'll bring this down. Okay. Okay, back with the 5 by 3. If we recall, these points here were the ones which we should not choose if we want to maximize the number of points that are covered by our dominoes. So just for example, I'll pick the top left corner up here. Then if we're running the tile completely, we'll either pick this domino here or here. So we'll just go here to start. And then as we can see, we're left with a 4 by 3 lattice left over, which is tileable because it's even and it's square. So that's how it works for points that are not of that set, at least for small M and N. I would like to generalize it for all M and N in the future, if possible, and see if the condition holds. But that's a project for later, I believe. Yeah, and that will conclude what I've found on my own. So I'll move on to the conclusion slide here. So what I've shown in this lecture, calculations are difficult for large M and N if we're using the generating function that I showed earlier. Estimations are upper bounds, and speed up calculations. 2 by M rectangle tilings are the same as the Fibonacci sequence, and incomplete tilings have the potential for optimization, at least in terms of picking points. Yep, and thank you very much.
Any questions? Let me add some comments.
Okay.
If you want to sit down, I can. Okay. So the big item in terms of these discussions is we have some quantity that we want to compute. And just because you have a formula does not mean that you can actually do the calculation in any reasonable amount of time. So, we had a formula that he shared. Here's the formula that counts how many lattices there are. How many coverings there are with 2 by 1 dominoes or dimers, and all we have to do is put in M and N and then just go through and do this calculation. This is a very painful calculation to look at. When you see something like this, what's your first thought to try to understand this? We have ZMN of ZZ prime is equal to this double product of this mess. What's your first reaction when you see something like this? You should have a Pavlovian response at this point. We have a double product. How might you try to understand a double product?
Look at only one product first.
You could look at only one product first, but whenever you see products, what should you be doing? Take logs. If you take the logs, the log of a product is the sum of the logs. And what you can do is by taking logs, you can actually convert these to Riemann sum approximations, which then become integrals. And so one way to handle this is you take a log, analyze it, and then exponentiate, and you get back to where you started. And so that becomes a really good way for attacking something like this. And you can see that as we're moving things up by very small amounts, that should look a lot like a Riemann sum, which can be well approximated by an integral. Integrals are much easier to do in closed form than sums, and there's a hope of getting something. Well, if you want a Riemann sum to converge to an integral, what must be true about your Riemann sum? So the way a Riemann sum works is we start off with here we have our function. We chop it up into pieces, and then we approximate the area under the curve. And so if you want to have a good approximation, what should be true? You want smaller and smaller. You want more and more pieces. So then you would do refinements, and you would have smaller and smaller. So when you look at the original formula that we were given, I want m and n to go to infinity. As m and n go to infinity, the corresponding sums that arise after we take the logarithm are going to become well approximated by integrals. If I give you a complicated function and I just have one box to try to estimate the area under the curve, I'm not going to do a great job. But if I have 1,000, a million, a billion, a quadrillion, and so on and so on and so on, the more subdivisions I have, the better approximation the integral will be to the sum. And so there's a hope of being able to get an answer to a problem like this if we have a huge number of pieces. So that means, in the limit as m and n go to infinity, we should be able to get some sense of what's going on. Now, if you remember what we did when we did Stirling's formula estimates n factorial as n to the n e to the minus n squared of 2 pi n times the quantity 1 plus 1 over 12n plus ... 1 over 12n is very small relative to 1 if n is huge. If n is 10,000, this is 100,000th of the main term. That doesn't mean that in isolation it's a small number, right? Which is larger percentage-wise, 1/10,000th of my net worth or 1/10,000th of Elon Musk's net worth? Which is a larger percentage? So 1/10,000th of his net worth as a percentage versus 1/10,000th of my net worth. Which is a larger percentage? It's the same. It's both 1/10,000th. Now, if you look at the actual magnitude, 1/10,000th of his net worth is still a very large number. Sadly, 1/10,000th of my net worth is not. Okay, so percentage is important, but for some things you really care about what's the relative magnitude. So when we do Stirling's formula, we could be off by a number that's quite large, but it's going to be dwarfed by the main term. And so when we're trying to analyze a quantity like this, frequently just trying to get the main term is enough. It would be great to have as accurate a formula as possible, but frequently the main term is all that matters. And what you might do is you might take your guess and you divide by the true answer and you see what happens in the limit. And as long as your main term is close to the true value, in the limit, this ratio is going to go to 1. You're going to essentially see everything. And again, on an absolute scale, you might be off by a little bit, but on the scale that really matters, you will have a great idea of what's going on. So the hope is that there are ways by taking logarithms, converting this to a sum, converting that to an integral, evaluating the integral in closed form. The hope, the prayer is that we can actually get this in closed form. And there's a bunch of games you have to play, but it turns out this can all be done. And so we can actually evaluate this in the limit as m and n go to infinity. So for very large m and n, we have something that makes sense. Well, what are we really looking at? When we look at the generating function, we're looking at all pairs n2, n2 prime. So n2 is how many horizontal, n2 prime is how many vertical. So they go from 0 to everything, right? Maybe we have nothing that's vertical. Maybe we have everything that's vertical. This is a finite sum. If we take z and z prime, I think this prime is actually supposed to be a prime over here. It's supposed to be z prime. Let me see if I can add that. Okay, so if we take z equals z prime equals 1, then it's just going to count all the different configurations. And so when n2 equals mn over 2 and n2 prime equals 0, that means everything is horizontal. And that counts how many tilings are there when everything is horizontal. Can anybody tell me how many tilings there are when everything is horizontal? Or can you give me bounds on how many tilings there are when everything is horizontal?
There's 1/2 full tiling.
Tilings. So how many ways can I do where everything is horizontal? Can you give me an upper bound?
1.
1. If I have an even number of columns, then I can do with everything is horizontal. And there's only one way to do it. If everything's horizontal, I have no freedom. If I have an odd number of columns, I can't do it because my last one would have to go vertical. So we know in the case where everything is horizontal, this number is either 0 or 1. And it's very easy to figure out which it is. Conversely, it's very easy to figure out the case of 0 and then mn over 2, where everything is vertical. The intermediate ones are much harder. For a lot of problems, we don't care how many ways we have of each possible configuration. We just care how many are there total. I don't care how many times we have 30% are horizontal and 70% are vertical. I just care how many ways are there to do this. So while it would be nice to know these values for each pair n2, n2 prime, frequently all we care about is the sum. And we can figure out what the sum is by taking z equals z prime equals 1. And so to do that, we need to somehow estimate this painful formula that they get, and that's where they're able to get something in the limit. And then the hope is that if m and n are reasonable, not too small, then the limiting approximation is a good estimate for the value we care about. And so it would be good, we could try programming this in Mathematica and then report back to the class, what values do you get for, say, mn equals 4, 5, 6, 7, something like that, and see how accurate is the estimate to what we're predicting. And again, this is supposed to be true in the limit as things get very, very large. It's not necessarily going to be a good approximation for small values. And whenever you're doing something like this, you always want to figure out what's the right quantity to look at. We also want things that will have a reasonable answer in the limit. So notice we're taking this to the 2 over mn power. This turns out to be what comes out in the calculations, but this gives us a hope that this quantity will make sense in the limit as m and n go to infinity. As your lattice gets larger and larger and larger, do you think there's going to be more or fewer ways to cover? What do you think? As the lattice gets larger, should there be more ways or fewer ways? More. And so this quantity should be growing with mn. And so when we take the 2 over mnth root, the hope is that that will become something that will be nice and well behaved, and that turns out to be the case. So you talked about a bunch of different coverings. So here is a problem related to the Fibonacci's. Although initially it doesn't look like that. So I'm going to give you 2 types of boxes, an empty box and a box, a domino that's filled in the first spot, but not the second spot. Okay, so I have 2 types of dominoes, a 1x1 domino that's empty and a 2x1 domino that has the left part filled and the right part unfilled. And what I want to do is I give you something that's 1 by n. How many ways are there to tile this? So let's let an be the number of ways to tile. So any thoughts on how many ways there are to tile?
Well, it would be an equals an minus 1 plus an minus 2. Similar to the 2 by n.
Right. So if we start off by putting in the blank 1 by 1 tile, in that case, we now have something that's of size n minus 1. And by definition, the number of ways to do that is an minus 1. Or we could start off by putting in, the 2 by 1 tile where the left part is filled. Okay. Are these the Fibonacci numbers? Well, we need to get the initial conditions. What's A1? It's just 1. What's A2? Why 2?
Because you could either have 2 of the singular boxes or 1 of the double box.
Good. So there's 2 ways to do that. So the sequence is 1, 2, 3, 5, 8, ... So we get the Fibonacci numbers. It turns out this is related to an interesting property of the Fibonacci numbers. If you define the Fibonacci numbers like this, and I've done a lot of research with my students on this, you have a beautiful result called Zeckendorf's theorem. And as we're nearing the end of the semester, this is a good opportunity to start talking to people about types of research projects you can do. We have a wonderful summer REU at Williams College, Research Experience for Undergraduates, the small program. So Zeckendorf's theorem says, if we define the Fibonacci's to be the sequence 1, 2, 3, 5, ... every positive integer has a unique decomposition as a sum of non-adjacent Fibonacci numbers. So somebody give me a number that's not too large, not too small. Not too small. Give me something at least 50, no more than 200. 73. So the Fibonacci's are 1, 2, 3, 5, 8, 13, 21, 34, 55, 89, 144, ... And you gave me 73? So what we're going to do is we're going to decompose 73 by using the greedy algorithm. What's the largest Fibonacci number less than or equal to 73? So I can write this as 55, and what's the remainder? 18? And now I'll write that as 55 plus 18 is 13 plus 5, and we're actually done at this point. So the greedy algorithm is going to give us a decomposition. We throw away the largest Fibonacci number we can, look at what's left over, and repeat. When we did this, what if when we decomposed 18, we got the number that was adjacent to 55? Then we were a moron, because we're supposed to throw away the largest Fibonacci number we can, less than or equal to 73. If when we decompose what's left over, we got the number next to 55, we could have thrown away their sum. So if you just think about this a little bit, you'll see that when you're doing this, you can never get 2 numbers that are adjacent. Because if they did, you could have thrown away their sum at an earlier stage, and that contradicts. So it turns out, if you think about what's going on, so let's look at the numbers. So we have, in this case, we have 5, we have 13, and we have 55. Okay. I'm going to write these as, here is a block of length 2. here's a block of length 2, here's a block of length 2, and I'll use a different color. Here's a block of length 1, block of length 1, block of length 1. Oh, 21. Let's split it up. That's bad. So what do you notice? How is this related to what we've been discussing? Yes.
Why did you group 34 alone instead of 34 and 55, similar to the leaves?
So
5, 8,
the numbers in my decomposition are 5, 13, and 55.
Oh, you just
So
grouped
at
it
5,
according-
13, and 55, I put a block of size 2 with the left point taken. And for all the others, I put a block of size 1. How is this related to what we were just doing? It's a tiling. So it turns out our result on tiling is equivalent to results of writing numbers as sums of non-adjacent Fibonacci's. So there's a one-to-one correspondence between legal tilings and decompositions. And then you can talk about generalized decompositions. You can do this in other things. And what this shows you is connections between various parts of mathematics. A lot of times it's very hard to do certain calculations, but if you can show that this is related to something else, the calculation becomes very easy. I've now related a tiling problem to a problem involving Fibonacci numbers. And so you have the ability to go back and forth between various things like this. I don't have my laptop on me, so I can't. Oh, well, here's a fun problem. So we did the generating function for the Fibonacci's in this class, or no? I thought we had. Do we do this, is the sum n goes from 0 to infinity of fn x to the n, where the Fibonacci numbers are defined as 0, 1, 2, 3, oh, sorry. 0, 1, 1, 2, 3, ... Did we do this?
I think we did.
All right, so what you can do is you can look at, fn plus 2 is fn plus 1 plus fn. So if I give you the sum, say n goes from 2 to infinity of fn x to the n, this is the same as the sum n goes from 2 to infinity of fn . Let me change indices a little bit. I'll have my sum starting off at 0. And I'll have this as fn plus 2 x to the n plus 2. Does everyone agree that this is fine? I've just shifted my index. This is the same as the sum n goes from 0 to infinity of fn plus 1 xn plus 1 plus the sum n goes from 0 to infinity of fn x to the n. Well, this thing over here is just our generating function g of x. This one over here, so this should be x plus 2, and this should be x plus 2. So just be g of x, x squared. And this would be essentially the sum n goes from 0 to infinity of fn plus 1, xn plus 1 times x. Well, the only term I'm missing is I'm missing the f0 term, but the f0 term is just 0. So I get over here, this is just x times g of x plus x squared g of x. And over here, this is going to be g of x minus the n equals 1 term, which is just x. So you can solve for g of x. You get g of x is x over 1 minus x squared. You can write the denominator as 1 minus alpha x, 1 minus beta x. You use partial fractions. And you end up getting your expansion. You get your Bernays formula. You get the nth number is 1 over root 5, golden mean to the n minus 1 over root 5, 1 minus golden mean to the n. And now if I give you something like g of 1/10, this is the sum of fn over 10 to the n. we actually have a closed form expression for that. That's just g of 110. So this shows you some of the powers of generating functions. All right, this is a good place to stop. Have a good rest of the day.